Hi everybody, it's Mr. Molikash. This is our Week 10 video for Math 171 for Johnston Community College. Here's my email address if you're watching this video and you have a question you want to shoot to me. There's quite a bit of stuff to talk about in this week's video, so we'll just get right into it. The Section 2.3 in the Julie Miller book has a couple of things you'll need to do. One of them is finding a polynomial the equation of a polynomial given the degree and the zeros, right? Given the degree and the zeros. Okay, so and the zeros are real numbers. So let's, for example, let's say that we have degree 3 and the zeros are x equals 1, x equals 2, and x equals 3. Well, the zeros make factors of the polynomial. So you can start out with f of x equals 3 different factors, and these are called linear factors. Okay, our first factor is a number, is from this number x equals 1. So if we use x minus 1, we can safely say that this is a factor because 1 makes this factor equal 0. The other factors would be x minus 2 and x minus 3. And as you can imagine, if these numbers are negative, these would be x plus whatever. You know, use the opposite of the number so that the resulting factor is 0 when you plug the number in. So how do we find the equation of the polynomial? Well, we just multiply this stuff together. So I trust that you know how to multiply binomials together, so I'll leave the details out of this, but the answer to this is x squared minus 3x plus 2, right? And you can only multiply 2 of these at a time, right? And so then, you know, you distribute and you get x cubed minus 3x squared, and then we'll distribute the minus 3x, so that's minus 3x squared plus 9x, and then we'll distribute the positive 2, and it's positive 2x minus 6. So when we add all this up, we get f of x equals x cubed minus 6x squared plus 11x minus 6. And then, you know, you can always go into Desmos and graph this and then see if these numbers are really the x-intercepts of the function, and that's a good way to check your answer. So another thing we'll have to do with polynomials this week is what's called long division and synthetic division. So, okay, you can see that these 3 factors multiplied together make this thing, right? So if I take this big long polynomial and I divide it by any one of the factors up here, I should get the other 2, right? So what we're going to do is actually, in this next example, I'm going to do this problem. I'm going to say, what's the result if we take the polynomial x cubed minus 6x squared plus 11x minus 6? And what if we divide that by x minus 3? Well, you would expect that from our previous work, if x minus 3 times this quadratic equals this, that when I divide this factor into this polynomial, that this would be the answer. So this is what we're going to expect the answer to be right here. You can also, like, for example, you know, what happens if you multiply 6 times 2? You get 12, right? So if I take 12 and divide by either one of these factors, I should get the other one, right? If I do 12 divided by 2, I get 6. So that's kind of what I'm expecting to happen here, right? This big thing is like the 12, and these 2 things are like the 6 and the 2. Okay, so, all right, here we go. The first way to do this is called long division, and this mimics, by and large, the way you would do long division with numbers, without the variables. But it's very important when you do this to make sure that if you're missing a term that you put in 0 for it. Okay, So if this were x cubed plus 11x minus 6, I'd have to put a 0 x squared. None of the terms are missing. We have constant, linear, quadratic, and cubic, and in here we have constant, linear. Okay, so without any further ado, I'm going to take this x minus 3 and put it on the outside of this big division bar here. And underneath we're going to have x cubed minus 6x squared plus 11x minus 6. Okay. It's very important when you do this to keep everything in columns. So everything I write in this column will be the x cubed terms. Everything I write in this column will be x squared terms. Everything I write in this column will be x terms. And everything I write in this column will be constants or numbers. All right, so what I'm going to do is I'm going to count how many terms there are in my divisor. This is called the divisor. This is called the dividend. At the end, I'll have the answer, which is called the quotient. And because of our work earlier, there should be no remainder. We'll talk about remainders in another example soon. So there are 2 terms in the divisor. So I'm going to go to the second term in the dividend, and I know that in this column I have to put x squareds. So the variable is going to be x, and the degree here is going to be 2. But what I need to do is I need to make sure that whatever number I put in front of this x squared, that when I multiply it by the coefficient here, I get the leading coefficient. So what number times 1 makes 1 is 1. So therefore I'm going to leave that a 1. Now the next thing I'm going to do is multiply x squared times x minus 3. And this is nothing more than like the distributive property. If you do this kind of thing, you know how to do that. So we're just going to do that. X squared times x is x cubed. I'm going to put it here because the x cubed goes in this column, right? X squared times negative 3 is negative 3x, and of course that goes in my x squared column. All right, so if you remember from long division, the very next thing you have to do is subtract these 2 terms from these 2. So what I do when I do this is I always take a red pen or highlighter or something like that, and I remember to change the sign, because subtraction is the same thing as adding the opposite. So I'm going to remember to do that every time I multiply a monomial in the divisor, in the quotient by the divisor. Okay, so when you do this, the leading terms should always cancel out. If they don't, it means you messed this up. The first term should always, 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 always cancel out. All right, so we're going to combine these and get negative 3x squared. And if you remember the long division algorithm, what you do now is you bring down the next term out of the dividend. Okay, now the game I have to play is, what variable goes in this column? It's x. What degree is it? It's degree 1. Everything here is degree 1. Now I have to ask myself, okay, what number do I put in front of this x? Well, whatever number I put there, when I multiply it by 1, I should get negative 3. So the answer to this is going to be negative 3. And I'm going to have to do that distributive property all over again. So negative 3x times x is negative 3x squared. I'm really excited when I see these 2 things match. They have to match always, 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 always. All right, negative 3x times negative 3 is positive 9x. Okay. Next step is remember to add the opposite. So I'm getting my red pen out and I'm changing these 2 signs. And these cancel out. Woohoo! Okay, so this is 2x, and I bring down the minus 6. And you can probably guess what I'm going to put here. I'm going to put a number, no x's. So what number times 1 makes 2? The answer is positive 2. When I multiply 2 times our divisor, I get 2x minus 6. And when I add the opposite, there is no remainder. Okay, so believe it or not, this is the answer that we were expecting from earlier. Okay. Now you might be asking me, hey, Mr. Molocash, what happens if I get a number here, right? Well, the number, okay, when you get a number here, this is called the remainder. Okay, and there's a couple of ways you can write this. You can say remainder whatever. You can say blah, 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 remainder 5 or remainder 8 or whatever. Another way to write this is the answer should always have the format quotient plus remainder over divisor. So in this example, the answer is actually going to be written x squared minus 3x plus 2. Remember, that was the quotient. Okay, the remainder right now is 0, so it's kind of ridiculous for me to put 0 here, but I'm doing it just for instructional purposes. And the divisor was x minus 3. So because there's no remainder, we can just simply write this as the answer, which is the reason I boxed this in. Okay, we're going to come back to this example later on in the video and do what's called synthetic division. But right now what I want to do is another long division example. So let's do this one. Let's say that we have x cubed plus x plus 1 divided by, I'm sorry, yeah, that's right. Let's put a 2 here. 2x cubed plus x plus 1 divided by x minus 3. All right, so what we're going to do is we're going to put x minus 3 on the outside here because that's our divisor. Very good. Underneath we're going to put 2x cubed, but there's no x squared here, right? So what I need to do is I need to hold a place for my x squared. I have to have an x squared column because I may have to deal with some x squareds in the problem. So everything has to have a place. If there's a term missing, we got to put a 0 in that spot and hold its place. Okay? So the linear one's there, the quadratic one is there, and here we go. So two terms. What goes in there? X squared. I'm in the x squared column. So I have to ask myself, hey, what number times 1 makes 2? So I'm going to put a 2 there. And I'm going to distribute, just like I did in the previous example. Now, hopefully you can see why it was important to put this here, because otherwise there would be nowhere to put the 2x squared in the problem, right? Okay, remember to add the opposite, or subtract if you will. These cancel out, yay. This is 6x squared. And this is plus x. I'm only bringing down one term at a time, okay? That's important to do. So what we're going to do now is we're going to put an x here, and we're going to ask ourselves, what number times 1 makes 6? The answer to that, of course, is 6. And we're going to distribute. I'm speeding this process up a little bit because this is very repetitive. You just keep doing the same thing over and over again, right? So this is 19x plus 1, and we have to put a number here, right? So what number times 1 makes 19? And the answer is 19. And don't get freaked out by the fact that that's a two-digit number. That's okay. You can have 2 digits. You can have as many digits as you want in a term, right? So 19 times x is 19x. 19 times negative 3 is negative 57. And this time when we add our opposite, we're happy about one thing, and that is that the leading terms cancel out. But the other thing is, uh-oh, we have a remainder. Uh-oh. So the way to write this answer again is to do the quotient, which is the top part here, plus the remainder over the divisor. Okay? Now, you might be asking yourselves, how do I check this? How do I know that this is right? How do I check this, right? So one thing you can do is you can take, and I'm not going to work all this out, but you'll have to trust me and do this on your own. You can take your dividend and multiply by the quotient. Okay? So these two factors don't multiply to make our original polynomial, but if we add back the remainder, it will work out. And so what happens is, maybe I will work this out. I know this is going to be a crazy long video, and I'm really sorry about this because there's a lot to cover, but it's important that you understand what's going on. So that's minus cubed squared, and then that's minus 57x, and then this would be minus 6x squared, and then that would be minus 18x. I hope I did this right. Nope, I sure didn't. Let's try that again. 2x cubed plus 6x squared plus 19x. Sorry, I had a dyslexic moment where I multiplied the 3 and the 19. All right, so that makes this, that makes that, and there's the negative 57 right there, right? And then we want to add the 58 later because that was our remainder, right? Okay, so that cancels out. That should have been plus 19x earlier, so this makes plus x, minus 57 plus 58, and what do you know? We get our original divisor because this makes positive 1. So this is the way to check the answer if you have time. And I know this is kind of crazy long, so I apologize for that. But okay, what we're going to do now is we're going to do this thing called synthetic division. And synthetic division is a good thing to use if the divisor is linear with leading coefficient 1. So both of the examples that we just did actually had that kind of divisor, right? The leading coefficient was 1 and this was linear, x to the 1. Okay, the one before that we were dividing by x minus 3, right? So we're going to do the same problem all over again that we just did a little while ago, and you might like this process a lot better because well, you'll see. This is going to go a lot faster, and in the beginning you're not even going to write down any x's at all, just numbers. So what you do is you find the 0 of this divisor. The 0 of the divisor is x equals 3. So this number goes into a little box here like this. Okay? So then what you do is you write down the coefficients. You want the coefficients of the dividend. And remember, you have to hold a place value for any number that's missing, right? So there was no x squared. We have to put a 0 in for that. But again, just the coefficients, right? 2x cubed, 0x squared, 1x, and 1. We're going to skip a line under this and draw a horizontal line. And then what we're going to do is we're going to copy this 2 down under the line. All right, now you may have to replay this video multiple times to really get this process, or do several problems to get good at this. But what you do is you multiply the number in the box by any number down on the bottom and put it in the next column above the line. So 3 times 2 is 6. And then what you do is you add the column together, and you just keep doing that process over and over again. So 3 times 6 is 18, add, you get 19, 3 times 19, you get 57, and 58. Okay, now the number at the very end is the remainder. See how much faster I got to that remainder than I did earlier, right? Same remainder, right? And you might remember that the 2, 6, and 19 were the coefficients of the quotient, right? So these are the coefficients of the quotient. Now, you don't have to label all this stuff when you're actually doing a problem, but I'm just doing this for instructional purposes so you can see what all this stuff is. Now, we have to figure out the degree of the quotient. And the degree is simply going to be found by dividing the leading terms. So 2x cubed divided by x is 2x squared, and then we just go down from there. So this is plus 6x, this is plus 19, and then this is the remainder, which we write over the divisor, and we're done. So that's the same answer that we got here when we did long division. And you can see now that the long division process is, got a lot more stuff going on and writing things down, and it goes a little bit slower because you have all these x's and things to keep up with. The only drawback to synthetic division is that you have to have a divisor that's linear, and you should be doing this with a leading coefficient of 1. If it wasn't starting with a 1, there is a way to do this where you can multiply and divide back again to make it 1 and kind of trick the process out, but I would advise against that. I would only do synthetic division if you're dividing by 1x plus or minus a number. Okay. All right. So there's the 2-3 part. Now, the reason why we're doing this is because maybe you have a function called a rational function. This is 2.5. This is section 2.5 in the Julie Miller book. Okay, so a rational function is one that you have a numerator. So you have some function on the top. We'll call this numerator of x, and we'll call this some other function on the bottom. We'll call this the denominator of x, right? And both of these are polynomials. Okay, so some freaky things happen when you divide by 0, right? You're not allowed to divide by 0. We talked about that before with domain and such. So we kind of have to find out where the function is possibly has a 0 denominator. So what might happen when you have a denominator that's 0 is you might have what's called a vertical asymptote. So when the denominator is equal to 0 and the top is not 0, you get a vertical asymptote. And I'll show you what that is in just a minute. It's a vertical boundary line that the graph can't touch. Okay. Okay. At x equals whatever number this is, right? Whatever number makes this happen. When the bottom is not 0 and the top is, you get an x-intercept at that x value. Okay. And you might be asking, well, what happens if they're both 0 at the same time, right? You shouldn't see any examples of this, but just in case you do, you get what's called a hole in the graph. And what that is that there's like an open dot where everything in the graph is there, but there's like this one open dot where there's a hole missing. So this is like a missing point. Okay, at x equals whatever. So let's look at a couple examples of this. One example is, we'll say f of x equals a constant number over a linear. So let's say 2x plus 5, right? Well, the top is never going to be 0, right? So we're not going to even look at these last two things. The top is not 0 at all. So there's not going to be any x-intercepts or holes in the graph. There's only going to possibly be a vertical asymptote. So this is where I get to show you what a vertical asymptote looks like. So the denominator, we're going to find out when that equals 0. And we can solve this pretty easily. This is x equals -5/2, right? So this means that this is the line, the equation of a linear vertical asymptote, and by linear I mean vertical line. Okay, so what happens in the graph is that at x equals -5/2, which is let's see, there's 4/2, there's 6/2, so there's a boundary line here. I'm calling this like a dotted line, maybe like an invisible force field or something like that. And when the graph is not going to touch that line, So there's what's called a discontinuity. There's some stuff on the left side of this, or some stuff on the right side of this, but this number is not in the domain. So the domain of our function from earlier, right, would be negative infinity to negative 5/2 union negative 5/2 to infinity. So there's stuff to the right of the asymptote or stuff to the left of the asymptote, but well, there's no y value when x is negative 5/2 because you get 6 divided by 0, which of course is undefined, right? So what might the graph of this look like? Well, from here, what you have to do is a couple of things. There's a horizontal asymptote. Whenever you have a constant over a linear, there's a horizontal asymptote. So there's another one of these dotted lines that goes this way at y equals 0, or otherwise known as the x-axis, right? So the x-axis is another asymptote. The graph can cross over. There actually are functions where you can cross over an asymptote and come back to it, and it still passes the vertical line test. You can't touch a vertical asymptote, at least not usually, unless you have some crazy piecewise function or something. This one is not going to touch this vertical asymptote, and it's not going to touch the horizontal one either. But in general, you can actually cross over this and come back. So what really happens, you'll find out in calculus, is what an asymptote is the end behavior gets close to this line. And then as we get close to negative 5/2, the function gets close to that line vertically. Okay, so there's two boundary lines here, right? So what we're going to do is we're going to pick points on either side of the vertical asymptote. So I'll pick some extra points. Say maybe x equals 1, so that's over here, and then maybe, you know, negative 3. So when x equals 1, f of 1 is 6 over 6/7, right? And when x is negative 3, let's see, 2 times negative 3 is negative 6, plus 5 is negative 1. 6 divided by negative 1 is negative 6, right? So if we drew the graph of these 2 points, we have negative 3, negative 6, which is right there. And then we have 1 and 6/7, which is just a tad under positive 1, right? Okay. By the way, the y-intercept is when x is 0, so we could have just as well put 0 in there and we would have got 6/5. But so yeah, 6/5 is a little bit bigger than 1. So okay, so what's going to happen is you know that the graph is not going to touch this line, so but it gets close to it at the end, right? So what's going to happen is we're not going to come back down, we're going to go up and approach this line like this. So this is one part of the graph, and then the other part of the graph looks like this. Okay, and you say, well, how do I know that that looks like that? Well, because the graph has to get really close to this vertical asymptote. The closer I get to negative 5/2, the closer the line gets to that asymptote, and it doesn't make sense for that to come up here and then bend back again, right? There's no weird behavior like this. So that's pretty much what the graph looks like. Okay, so that's kind of what happens with a constant over a linear. There's other examples of this where you have to do a linear divided by a linear. So we'll go through that very quickly. And there's even what happens with a quadratic numerator denominator, just finding out what the asymptotes are. So pay attention in ALEKS. But if you have a numerator that's linear, let's say we had something like 2x plus 5 over x minus 3, right? We find a couple of things, right? We find out where the top is equal to 0 when x is negative 5/2, okay? We'd find out when the bottom is equal to 0. That's when x equals 3. So these don't equal 0 at the same time. So there's no hole in the graph. But when one is 0, the other one isn't 0, right? So when the bottom's 0 and the top isn't, right, this is a vertical asymptote. I'll just abbreviate it VA. All right, when the top is 0 but the bottom isn't, we get an x-intercept. So this is an x-intercept. Okay, but another thing that we have to pay attention to is the horizontal asymptote. And I'll abbreviate that from now on, HA. Yeah, you can laugh if you want to. But whenever the degree of the numerator matches the degree of the denominator, like this is x to the 1 and this is x to the 1, okay, what you do is you divide the leading coefficients. The leading coefficients are 2 and 1. So I just divide those numbers and I get 2. Okay, so I get y equals 2 over 1, or just y equals 2. Okay, now armed with all of this information, I can draw the graph, right? I can draw a graph, so let me quickly do that. Okay, so y equals 2 is a horizontal line. That's a horizontal asymptote, actually. X equals 3 is a vertical asymptote. And I'm dotting these lines because they're not actually part of the graph. They're just kind of guidelines that help me draw the graph. And then there's an x-intercept at -5/2, so that's right here. Okay? Okay. So right off, I know what the graph is going to look like. It's going to kind of have this part up here and this part down here. And by the way, if I put 0 in for x, I get 5 over -3, which is like 1 2/3. So the graph definitely does this kind of thing. Okay, it looks very similar to the one that we just drew, in fact, but it's moved up a little bit. So that's kind of what's going on there with linear over linear. Linear meaning degree 1, right? So you could have quadratic numerator or denominator, but the idea there, if we go back to the first example that I did, the reason why this is y is equal to 0 as opposed to dividing the leading coefficients is it's really cool. I could have gone back and put 0x plus 6, right? So that the degrees have to match. And then what happens is the leading coefficients are 0 divided by 2, which is 0, right? So what happens is if the degree is bigger on top than on the bottom, and I'll kind of leave you with this one. Let's say we had y equals x squared plus 2x plus 5 over x minus 3, right? I'll tell you right now, the top doesn't factor, so there are no zeros that are in common on the top and bottom. So this would be a vertical asymptote at x equals 3. There'd be a y-intercept at -5/3, right? X-intercepts are kind of hard to find. You'd have to use the quadratic formula to set that equal to 0. But the main reason I put this up here is for the horizontal asymptote, right? So what happens if I put like 0x squared down here? Well, when you divide those leading coefficients, what's 1 divided by 0? Undefined, which means there is no horizontal asymptote. In fact, what you find out about that is if you do the long division or the synthetic division, if you do this problem like we did earlier in the video, the quotient part of this is a line, and this line would be called an oblique asymptote. Okay, so if you want to go do that on your own, you can graph this where you have like a slanted dotted line instead of a horizontal or vertical one. Okay, but that's all we kind of have time for today. Sorry this video is so long and there's a lot going on now that fall break is over. But again, if you have any questions, feel free to contact me there's my email address, or leave me a comment in the discussion board. Thanks so much. Have a great week.